Hello, everyone. Today we'll have a talk from Professor Peter Chen. He's a professor at the University of British Columbia. Peter did his PhD at Columbia University, where he worked with physics, with computer graphics, machine learning with physics, etc. And he works really hard on how to mix physics and machine learning. So now, Peter, all yours.
Awesome. Thanks so much. Yeah, so I'm glad to really be here. Like I said, I've met lots of impact folks. Obviously, Daniel was part of HGI, but also Adriana was here as well. We're Adriana and we overlap at Columbia and MIT. So really excited to actually be here and see this wonderful facility that you guys have. And I am from Vancouver. This is actually where I live. So also where the school is, UBC. So I was just talking to Daniel, we're also right next to the ocean. And here we're also kind of on the mountain-ish. There's actually a cliff here. So we have lots of forest as well, but different kind of forest. You guys have kind of little monkeys here. We have big bears over there, but they all live in, the forest. And speaking of Vancouver, we're also hosting a World Cup this year. So if any of you guys want to visit, let me know. Also bought you guys a little gift, like a soccer-shaped World Cup. So I'll keep it here. With that, let's jump into business. So a lot of the thing that I do is kind of like simulating something, and these days we simulate for robotic stuff a lot. And you can think of this as kind of like a word model, right? In some way, simulation is a type of word model, right? Meaning given an action, right, on this joint here, what would actually happen in the world? So why do we need these simulations or these word models? It's because obviously these robots, you can do them in the real world, but they're very costly to operate. Instead, simulation offers an affordable and scalable way of evaluating your robot, for example, or for training your robots directly in these simulations. Also useful for model-based control, right? So and also useful for design stuff, right? Here's a real robot. Here's the simulation. Actually, I was just on call this morning for like 1 hour as Daniel and I, we were walking next to the lagoon, and we're sort of talking about these projects. How can you actually design better robots using the simulation? Design better shape, for example, right? So all in all, like these simulations, right, so sort of serve as the data engine, right? So in this case, because in the simulation platform, you can easily, change the materials, the lighting, and allows you to try different interaction. Therefore, enable these learning process. And again, why do we have to do this in simulation? And a lot of it is because we want to scale up the data, right? Because if you do in the real world, you can't really, sample a lot, right? Let's say you're doing reinforcement learning, but if you do this in simulation, it's very cheap. You can sample lots of time. Okay, so how are these simulations done? These simulations are traditionally done, using these solvers, right? Like these classical numerical ODE or PDE solvers. Typically, they're, you write down the equations, and then you sort of, solve it numerically, right? So this is sort of traditional computer graphics approach, right? Where I learned a new term from Daniel today, vintage computer graphics, right? So this has been sort of how we, in computer graphics, we model the geometry, we simulate it, all using sort of like the first principle approaches. These approaches are good, but they are sort of have limitations, right? Otherwise, I won't be here at iClear, right? I would just stay in my comfort of computer graphics community, right? So what are the limits, right? Accuracy, right? For example, modeling, has, the equation can have, errors, right? But also the solver can have errors. And another is, speed, right? These things generally are kind of slow. But really, the biggest problem, right? These are sort of in graphics, people will talk about these anyways, but really the hard part is this accessibility part, right? Meaning that like it's very difficult to actually set up something. Sure, you can, spend like months to set up a movie, right? I used to work at Weta Digital where we work on the Avatar movies, right? Sure, you can make one shot looks really nice, but it takes lots of efforts just even to make one shot, right? It's not a very scalable approaches, right? So that's sort of these traditional approaches are not very accessible, right? Not like, your ChatGPT, right? You can just enter something, it give you something. These traditional approaches are very fragile and requires lots of tuning and domain knowledge. So this is probably, what I think is the biggest bottleneck of these classical approaches. And obviously, you complain these problems to your colleagues, maybe we should use end-to-end neural network to do these things, right? It makes some sense, right? Maybe they are generally good at curve fitting. So I give these talks in mechanical engineering department, computer science department, math departments. Typically, when I talk about this in a math department, mathematicians be like, no, neural network is not accurate, right? So what I mean by here is that it can fit your data really well. That's what I'm trying to say. I'm not trying to say it has, second order convergence, right? These are two separate things, if you think about it. But anyways, the point I'm trying to say is that they can fit your data really well. And they're, relatively fast, right? This is, again, something that would, people will say no, because these neural network requires giant compute, right? But the problem is, it's cheaper and cheaper. So why not use giant compute? Why do we have to use those old CPUs, right, that we are used to in traditional computer graphics? And accessibility, this is really I think this is the sort of the key part, right? Again, it allows you to just, I don't know, when you do your sound project, right? You just get the data and you can just train something, right? You're not really modeling the Helmholtz equation, right? You're not trying to understand the exact physics there, right? But you can directly just sort of train something and then try to use the model. So on paper, really, there are lots of upsides. But there are also downsides. So here, in this case, we're looking at a paper from, IClear paper, won the best paper award from DeepMind. So interestingly, the first author used to be a computer graphics person, Tobias Pofov. I don't know if you guys know him, at ETH, back when he did his PhD. But the point is, this is such a great line of work, with essentially replacing these traditional solvers, right? No PDEs anymore, just do graph neural network from one time step to another time step, right? So this approach does have its limitations. For example, let's say when we train on the training data here, right? It doesn't necessarily, when we say we want to swap this cube geometry to like a bunny geometry, right? So it doesn't quite work. In fact, when we tested it on after training, it really suffers from these generalization problems. So that's one problem that we've been seeing, right? Is if you just naively apply these neural network, you run into this generalizability problem because of lack of physical laws, right? So in this case, this equation, they were never really leveraged here. So that's why it doesn't generalize very well. So this is sort of back to why we need physics-informed AI, right? Maybe these physics will help us, especially in cases where the data is limited. So in this particular case, we're only trained on this data here, right? So there are two ways to solve this problem. One is to just train on lots of data, which I think is definitely a very exciting direction. But at the same time, certain problems just don't have a lot of data. For example, certain science problem. So in those cases, having these sort of physics-informed approaches really help, as we'll see later. So in the end, sort of, I really want to propose there like two sort of very different approaches towards modeling, right? People have been, contrasting these two approaches, for decades, right? So again, what we're trying to explore is sort of in the middle, right? Where hopefully you get the best of both worlds. You have the accessibility, accuracy, and speed, but also, generalizability, right? So again, these hopefully neural network and these equations, you guys can, be friends. But obviously, depends on where you want to land, right? You could land sort of more on this and add a little bit of physics, right? Or you can sort of land here, right? Where you're very, very lots of physics and add a little bit of neural. So this is sort of where my lab explores, these physics, mechanical parts, and these neural network data-driven parts. Therefore, the physics AI lab. And so today, I think most of the work I will talk about today is sort of this approach, where we start from the red and go green a little bit. So add a little bit of neural network here and there. Well, probably more recently, my lab has been more focusing on this approach, but which was kind of like why we have a paper at iClear. But today, I'm mostly talking about this traditional approaches, go from the red to the green. Any questions so far? All right. So, okay. So, yeah, again, so I publish mostly in computer graphics, but also in machine learning, scientific computing, robotics. So I'm a big believer on, what we do should be cross-disciplinary. So the first thing is sort of parameter identification, right? So, we know these physics simulations produce these wonderful results, but very often it's very difficult to figure out the input, right? In other words, maybe the geometry, right? The mesh, as well as the different complex material parameters, right? So the, how soft this thing is, right? How easily fractured this thing is, right? So this is sort of the challenge here. So traditionally, this has been very labor-intensive manual processes. What if we can directly infer these things directly from videos, right? The geometries and the materials. So this is sort of the approach, a line of work that we started in 2023, also at iClear, interestingly. This was actually in Rwanda. That was my first time in Africa. So it's kind of like old work now, right? 3 years have passed, lots of my thoughts have changed. But I'll present it anyways. So the idea is basically, from these videos, you can construct these pixel level laws and directly sort of inversely optimize these geometries and parameters. And, there's differentiable physics solver here. That is just your traditional solvers, but sort of implemented in a differentiable programming library. NVIDIA Warp, which we had a SIGGRAPH course in 2024 on how to use these differentiable spatial computing tools like Warp. So just differentiable physics, not necessarily neural network here. And with this approach, we can sort of infer the different material parameters of various, materials. Okay. And sort of more recently, we've been applying sort of the same approaches, right? Sort of from a video, you recover the material parameters, right? How soft, how easily fractured this thing is. But now, sort of doing this in robotics context is instead of using a vision signal, right? Kind of instead of vision signal, you use sound signals, right? But in this case, we're using these proprioception signals, essentially the joint, like how much force these robots feel on its joints, right? So it's another type of signal, but it's again the same type of sort of approaches is based on the signal, right? Because as a human, I know if I pick this thing up, right, I know this thing is heavier than this, right? Because my muscle feels it, right? My joint feels it, right? So that's sort of the idea here. And here's another example where we did, where we're trying to inversely identifying the properties of this box here. So this is after identifying the correct parameters. You can see that the robot and the robot motion is exactly following this robot motion, but this box here is simulated. And you can see that actually, so it's not a reconstruction, it's actually a simulation. So you can see that the box is actually move quite similar to the other box here, right? So this is quite useful for, again, training robots. I have a newer results where we actually show that we can actually fold this box fully autonomously by just training in this simulation environment. Okay, questions, anybody?
So the loss is completely differentiable, right?
Right,
so,
right.
Yeah. How do you guys did you did the formulation of the loss such that it's differentiable, right?
Right. Yeah. So, the nerve part was differentiable,
Yeah.
and the physics part is also simulation part is also differentiable. Yeah. So the entire thing is differentiable. Yeah. Like I said, it's sort of from 3 years ago, right? So I'm glad that community sort of really liked this line of work, but I also start to see the limitations. Every optimization takes forever. It's still a traditional approach, right? There's no zero neural network here, right? Maybe a little bit of nerve here, but that's still very traditional, like optimization, right? It's not a feed-forward neural network, right? It's not like VGGT, that kind of thing. And so it's kind of hard. It's also kind of hard to deploy in the wild. It's not like I just take a video of anything and just worked. It's very yeah, so it's not very robust. Yeah, put it that way. Yeah, so I think now sort of the approach is maybe we can train some type of feed forward neural network. Yes, there are lots of data like this, but then somehow given an arbitrary video, you can directly predict the material parameters. I think some more exciting direction to work in 2026. Does that make sense? Yeah. All right. So, so also so this is another work we did in 2023. So in this case, we were trying to, again, match these real world videos, right? So I think lots of the problem, I started to see more and more why these classical computer graphics pipeline is fragile when I'm forced to work on to match real world videos. So I think classical computer graphics pipeline is very useful for editing, creating a virtual world, but to actually really match the real world, right? In this case, right, we're really trying to match this real world behavior, right? This is sort of like a dough, like the dough to make pasta, right? We're just dropping it, and here we realize it's kind of difficult to match it, and the approach that we did here in this work is, these traditional sort of models, right? Like it's sort of you have all these kind of material models that describe different behaviors, right? It's kind of in rendering you have different BRDF, but in simulating physics you have these different material models. So hyperelastic models, plasticity, all that kind of stuff. And these models are sort of used in your PDE solvers, right? This is where your classical material model is. And in this work, what we did is replacing these classical material models that are hand designed by scientists with neural networks. And again, everything else remained the same. The PDE solver is still there. We're just replacing the material model with the neural network, right? So this idea is sort of maybe we can replace the solver had different parts, right? Maybe we can replace one part with a neural network and see what happens. And in this case, we're just replacing the material model with a neural network. This is from our ICML 2023 paper. And this actually makes a lot of sense because the material models have been empirical anyways, right? So Hooke's law, right? 1678, right? So this says the force on your spring is linearly related to the displacement, right? But obviously, it's not really linear, right? If you stretch it longer, it becomes nonlinear at some point in fracture, right? So a lot of these are phenomenological models anyways, empirical models anyways. So it makes sense to actually replace these models with neural networks. And as a result, having these neural material models makes the simulation more expressive and have bigger capacity to fit the real world videos. And what's really cool is that, after training, right, these neural material models, you can also directly swap your cube to a star shape and still works really well, right? So in machine learning language, right, this is called zero-shot generalization, right? You train on one shape and generalize to another shape, right? So this is the part I'm trying to make a point, right? This approach where traditional solvers, you replace only one part with neural network, like hybrid neural network PD approaches, versus the pure data-driven approaches that we talked about earlier, right? That's sort of the mainstream, school of thoughts in the AI community, right? So how are they different, right? So basically, if you're adopting this approach, right, you're dropping lots of things, right? You're dropping the conservation of mass, momentum, and energy, right? So lots of these physics sort of knowledge, you just drop it directly, right? So as such, right, so we saw earlier, right, it struggles to generalize to different geometries, right? But this sort of hybrid neural network PD approaches generalizes, perfectly. Also, in changing the initial velocities, changing the boundary conditions, let it simulate in longer time. And you can even couple them together easily, right? So again, because this approach is still very much using these traditional sort of pipeline, except just one part is a neural network. And even do these multi-phase behaviors. And train on 1,000 degree of freedom generalized to 1 million, right? So these features are clearly pure data-driven approaches don't work really well, especially when it was trained on relatively limited data, generalized to multiple objects, contexts. So in other words, in generalization is over 100 times more accurate than these pure data-driven approaches that do not keep the PDEs. What does this imply? By incorporating these physics into learning, you can use less data, smaller network, and also faster to train. Questions so far?
How fast compared to the pure data-driven version?
Yeah, it's again, right? It trains on less data,
Okay.
so it's really fast to train, like 10 minutes. Yeah, which is almost too fast to be useful, because yeah. Other questions?
I also have one question. So, what kind of information do you use? Probably like features that you extract with an network to determine what kind of equivalent of equation you would use. Because in normal, if you would go for like a normal physics approach, you would probably like choose an equation beforehand.
Yes.
Right? Because you know the material.
Yes. Yes.
And then you just apply it.
Yes.
Now we're trying to do something that is more general.
Yes.
So I guess that we need some kind of the network needs to be able to tell what kind of material is it you're working with. Right. And how do you tell that? Yeah. Well, how do you tell that?
No, so
that's the time steps.
So that's the fantastic part in the sense that again, this is a 2023 paper, right? But it's already an improvement in over traditional approaches in the sense that traditional approaches, right? When you see something, right, like this wire here, right, you have to manually pick a material model for this, right? This wire and this, right? They have to be, you have hand-tuned these different models, right? But with this approach, you can already kind of do this in an agnostic manner. Give me the data, right? The data is to track, you have to track the motion of this thing, right?
You have to track the motion.
Yeah.
Makes
So you
sense.
track the motion of this thing, right? But as long as you get the tracking of these guys, you can fit this model without actually need to tell this is kind of very rigid, this is very soft.
Perfect.
Right?
Because the motion depends on the material, right?
Yeah.
So,
So it's implicitly captured.
Perfect.
Yeah.
Yeah, that was exactly the question actually, because at first you needed to tell the model which kind of material you had, and I just wanted to know like how would you tell, not explicitly, but with the motion?
With the motion, yes. So it was
Thank you.
trained on the, Gaussian splats, for example. Yeah, the tracking. Yeah.
Thank you very much.
Yeah. Yes. Okay. So now to the sort of third part of my talk, which is these reduced order models, which is an OG approach towards ML for physics simulation. It has been around since 1987, and for sure in computer graphics as well. These basically the idea is these simulations are too slow, right? They are too slow. One of the reasons was because there are lots of spatial samples, right? No matter which basis function you use, right? You have a large degree of freedom, and solving the physics of the motion of all these guys are very expensive. So reduced order model approach sort of say high dimension data, no problem. I can just train a low dimensional latent space, right? You have an embedding of your high dimensional space, right? And after training, forget about your encoder, and you can just direct solve your physics in a low dimensional space and get your results in a high dimensional space. Makes sense, right? So we did a workshop last year called Reduced Order Modeling for Physical Simulation, from the classical to the neural. So this approach is usually you have your latent space, right? This Q, you can have a physical meaning. It doesn't have to have a physical. It can have a geometry meaning. Maybe it doesn't have a geometry meaning. Doesn't matter. But usually there you have a low dimensional latent space, and you have a manifold that sort of parameterize this high dimensional vector field here, right? These dots here, right? For example, it could be the velocity of this dot here, right? Is here. Velocity of this dot is right here. Blah blah blah. So this is prior reduced order models. You can do this using PCA or POD, and you can also do this using neural network, using autoencoders, right? So, both of these approaches, people have been explored extensively. But regardless of whether you're using neural network or using linear method, as long as you're adopting this sort of architecture here, you don't really have information outside the fixed degrees of freedom, at least not directly. And it's very difficult to train with data that has different resolution, or changing the resolution, after training. So you can't really do adaptive match sort of data. And if you can change the resolution, mesh, not to mention changing the geometry. So the key and not to mention topology, right? Like, let's say I want to punch a hole here, I want to make a cut here. So the key observation here is that this traditional reduced order module approach that has been around for 30, 40 years, it's built for the discretization of the continuous system instead of original continuous system itself. And these days we talk about these physics foundation models, right? And one important, if we really want to go there, we have to sort of have a new way, a new paradigm, such that we're not bounded by this discretization. So we sort of made one way towards that physics foundation model that is not bounded to a discretization. So again, same thing, low dimensional space here. But instead of sort of inferring a discretized vector field, you directly infer the continuous vector field itself. So this X could be arbitrary thing in your domain, right? So as such, you can obviously infer at arbitrary resolution you want and train with different resolution at the same time, and even change resolution over time. and even change the domain geometries, and even introduce topology changes. So basically, in theory, right, simply changing this architecture from the previous one to this one allows us to address all the challenges of the previous approach. Now you can train data on any discretization of the original continuous system. Obviously, when we started this line of work in 2023, this was the, we're using neural fields, right? Like kind of neural SDF kind of thing, right? It's very similar to neural SDF, right? So instead of a SDF function, and neural SDF, this Q here is kind of like represent different geometries, different shapes, but now it's sort of representing different state variable of your physics, right? So neural field makes sense, but really the point here is not neural field. The point here is this architecture. So in fact, later on, we'll figure out actually you don't necessarily need a neural field here, right? It's kind of NERF doesn't, like neural rendering doesn't need NERF, right? Gaussian splatting works for neural rendering as well. So in this case, discretization field representation is the key, not a neural network. And obviously, we really appreciate the community likes this type of work. Also started at iClear. So since I really like this conference, iClear, and whatever I publish at iClear, I'll extend it to SIGGRAPH. That's sort of my approach these days. So sort of the initial idea was at iClear 2023, and then we did computational physics paper and a series of SIGGRAPH paper, including the best paper award last year, as well as the best paper award on implementation last year. Because again, at SIGGRAPH, with a lot of time, it's just you have to polish the work, right? And so that makes sense. So maybe try some new ideas in other venues and really polish it in SIGGRAPH. Okay, so that's what the idea, right? And train on break the constraint of discretization, and after training, it was sort of you do these, but how do you actually predict physics? How to solve physics, right? The idea is you from low dimensional space go back to this high dimensional space, and still do a PDE solver here, and then project it back into your low dimensional space. Again, neural network only serves as spatial representation, right? So this sort of go back to what I talked earlier. We're not trying to replace the entire solver with a neural network. Here the neural network only asked to sort of give us a low dimensional representation. They're not asked to learn the dynamics. Dynamics still using PDEs. And PDE provides these temporal dynamics, which is very strong structure, right? So it allows for generalizability, as we'll see later. Okay, we're gonna go into the details here. Okay, so now let's see some results. So now, for the first time, we can actually train on different visualizations. One is fractured, one is not fractured. And what's really cool is that after training, you can actually gradually cut this thing. So again, gradual cutting never appears in the training data. The training data is either cut or not cut, right? So the reason why is that we can do this generalized to this gradual cutting is because we're only asking the neural network to learn sort of like a spatial representation, and the solver sort of takes care of like simulating the physics here. Again, previous discretization dependent methods, whether PCA autoencoders cannot handle data with changing geometries. Favorite example, swapping horses midstream. Do people ride horses here?
Yeah.
They do? Yeah? I don't know if they tried this. So the point is, we train on one geometry, right? Just poking this geometry at different directions. Now, after training, again, it was trained on the all, but now you can swap geometries, like crazy. So what's the point? Maybe there's no point. It was collaboration with Meta. They funded the research. At that time, they really wanted this because in VR, right, in metaverse. But now metaverse dead. Maybe the hope is doing this for robotics. So they're still giving us the funding. Now they ask us to design soft robots. Right? So word model, soft robots, right? So again, I think again, this line of work all comes from my sort of my line of thoughts in 2023 was like, I want to understand how far can we push if we just train on very little data, which is, sorry, question?
Can you go back to the method?
Method?
The method, the video you just showed on several. Yeah. So do you have a model of the skeletons of each object? You do have a model, explicit model of the skeleton?
Yeah, I have an explicit geometry, a mesh.
Oh, a mesh, a full mesh.
Yeah.
Okay.
Yeah.
Okay, thanks.
But it doesn't have to be a mesh, could be point clouds, could be any representation of the geometry, really. Maybe here's another example showing one model, but we can handle all kinds of geometries. So they sort of share the same low-dimensional latent space, but you can handle different geometries.
But what happens if the geometry cannot pass through this slot? It's the object is bigger than
Yes.
what is trained.
I know. Yeah. So, it was trained on the ShapeNet, right? And these ShapeNet objects have similar sizes. So, an easy way to break our work is to replace this thing with a much bigger version of the same geometry, and it would just stop working, I think. Would it? Maybe not. Yeah.
I'm afraid it's going to go through this plates. I don't know.
No, I think it can be stuck here. Okay, I take it back. I actually, at some point there was okay. So there are more details here. So when we did this work, right? It was trained on this simulation here, right? This is a data-driven approaches, right? You train on simulations. So then when we extend to this work, so that was 2023. When we went to this work, this is actually a data-free training. It was purely physics-informed losses, minimizing the Laplacian energy, all that kind of stuff. So that's why this thing actually generalizes better.
Right.
Yeah. It's not fit to that particular. So when you do data-driven, right, you're sort of fixed to this scenario, just poking this, right? I can't say throw it up, right? But in later on in this, when we did this, it was more like a data-free training. It wasn't trained on any simulation data. It was just trained to minimize a particular energy. Yeah. Okay. So, and obviously, there are lots of exciting things. I don't know if you're. So here in this case, we're trying to directly work with on-shape CAD model, no meshing needed, real time. So the point is, no meshing, right? We're not bonded to by using a particular geometry representation. And I don't know if you keep up with these newer AI sort of buzzwords like JEPA, word models, all that stuff. Yeah. So, and a lots of time, right? We have the low-dimensional latent space here, right? And solving the physics in low-dimensional latent space, right? So, so I think there are lots of room that we're currently just looking at how to connect this life work with these JEPA approaches. Yeah. Which I think is quite exciting, it doesn't, you're no longer bonded to a particular mesh, all that stuff. Okay, and you can do inverse designs, right? So not surprising, but again, that's the benefit of not being bounded to a particular mesh. Yeah, and drive home the point, right? This is, again, back in 2023, 2024, this fraction of bread, we can actually, for the first time, build this reduced order model for this type of data that has crazily changing topologies, all that stuff. Okay, yeah, so again, towards the foundation model for physical data, we want these kitchen sink ML models, right? Sort of, we talked about this earlier, right? You don't want to explicitly tell, oh, this is a soft sponge, I should pick this model, right? Oh, this is, like a leaf, I need to pick another model, right? So that kind of model doesn't really scale, right? So, but how can we actually go for such a model, right? So that's the goal. I think we're still quite far from it, but at least I want to make the point that whatever model we choose, you should be able to handle arbitrary geometries, and you should be able to handle arbitrary materials, right? So, and yep, with that, I would maybe end here. Again, this is from 2023. I don't know if I still believe in this. The point is I was trying to say, hey, these video models are okay, but they don't have mass conservation. They don't have momentum conservation. It's still a problem, but the training data is, the more data you train, the better it gets. But still, I think there are quite a bit of people, right, that sort of believe that these video models will not yet replace every existing 3D model. The eventual future of this stuff will come from integration of AI with ever-improving physical models, AI superpowers predictive system whose underlying equations are unknown or impractically expensive to evaluate, right? So founder CEO of Epic Games, we have lots of computer graphics colleagues working there, right? They recently bought Meshscape, Michael Black's, the human tracking, the SMP, all that stuff, right? So still people still sort of believe, you should still go from these red box sort of to the green box. And I think particularly, I think it's useful for situation where data is limited. But in terms of making films, making games, I don't know. I do feel video models are pretty good. But anyhow, we've also been trying to, like I said, more approaches from here to there, right? One of them is this iClear work where we did protein modeling, where we sort of, you have these AlphaFolds, you have these Bose generative models that give you these 3D structure of your protein. However, the physics might not be correct. There could be interpenetration, the bounds are not right. So we sort of propose a very lightweight differentiable solver that allows you to make sure you get physically correct results, both during training and inference. So that's one line of work we are quite excited about. And we're trying to sort of push everybody to do more science applications. So we're going to do a CRAP workshop again this year. So if anybody's work is related, sounds related, we would love to have you, present as well. Yeah, so, and I'm also organizing this synthetic data for robot learning, right? So again, trying to understand, where do we still need 3D data? Maybe even in robotics, I think robot learning, there's also this construct. Maybe should I just train on image data alone without these 3D data? So that that debate is still going, and we'll see. Thanks so much.
So more questions?
I have a
See if there are
question.
questions in the YouTube channel. But you can ask questions if you have.
Okay, so I was just curious. It's because, for example, you mentioned that you work back nerf, which uses nerf-based array, etc., right?
Right.
So we know right now that nerf has a bunch of problems,
Right,
including train time, etc.
Mhm.
If people start to use Gaussian splatting
For
instead
sure.
of nerf.
Right.
So I was curious if you like try something like in this direction or not.
Yeah. We have CVPR papers on replacing the nerve with Gaussians, right? It works better, but it's not like the limitations still exist, right? In the sense
Oh, yeah,
that
it's great.
per scene training, right, which is still expensive, and at the end of the day, where does 3D matter, right? Maybe in design problems they matter a lot. Maybe in manufacturing, where things are actually made 3D, matter. But in making films, not necessarily. Yeah.
Okay.
I also have a question.
Right.
So I'm very curious about generalization of some of these architectures and models, because say, for example, we go back to the sync example that we had, the sync example.
Sync, yes.
Yeah. So
Yes, go ahead.
yeah, okay. So yeah, the thing is, well, probably it's not always going to be the case that we're going to have motion track for every single object there, right?
Right.
And even so, like us as humans, even if we don't have even if we don't have a motion track for every object,
Right.
we do have some kind of intuition
Right.
for how the object is going to behave when
Right.
we pick it up.
Yes.
And I'm curious about like these next approach that is maybe a little bit more generalizable in this sense.
Right.
I think it has a lot to do with something that you said in the beginning of the presentation, which is looking at other types of sensors for the robot, right? Like how much some object weighs, for example, if you pick it up one way or another way, right?
Right.
So yeah, I think it's a very open question. It's just like, how do you see that for the future?
Yeah. So sort of going back to Daniel's question, right? Nerve, Gaussian splatting, whatever, right? Still trying to track everything, right? Everything over time in 3D, right? But do we really need that, right? At what level of sensor data do you really need? Yeah. So that's a great question. Yeah, and sort of going back to the reduced order model stuff I talked about, right? Obviously, when we developed the reduced order model, it's for making things faster or whatever, right? But essentially, reduced order model is a low-dimensional representation of the state, right? So the idea is because we can build a low-dimensional latent space of the state, we therefore shouldn't need tracking data of everything, right? So thereby, these sort of doing everything latent, that kind of ideas, right? So still, that's still quite exciting, remain unexplored. Yeah.
Doing everything on latent space, but then how do you encode it? Only by visually seeing it, by also picking it up? How do you encode it into the latent space?
Yeah, for sure. There's your latent space, it's kind of, you want to concave these feature variables together kind of thing, right?
Yeah, I'm very biased to that, but I always have this feeling that we haven't been able yet to actually mix vision with physical, spatial, with what people argue that is spatial knowledge, right? How we actually interact with the world. Right?
For sure, for sure. Do you mean like, like a tactile sensor kind of data where, like again, with human, we sense so many things, right?
We sense so many things.
Right. Yeah, for sure. Yeah. And that's sort of where these robots are heading, actually.
Yes.
Yeah. So they are building these robots that have sensor everywhere,
Yeah, it was a very open question. Thank you very
much.
much.
No. Thanks for, like I said, I'm changing my topics all the time, like in this past years, I mean, maybe I gave 5 talks and 5 different topics. The one I chose, this one is the safest one because this is how I got a job. But my other job topics are, do we still need physics informed AI? We're like, we will never close the sim to real gap. So that's what I'm trying to say. I like these open questions, because the field is open. A lot of times we don't know how to solve these things.
And something that I haven't said before, but very nice presentation. Thank you very much.
Yeah. Thanks so much.
Cool. So many cool projects. So much cool work. Thank you very much.
Yeah. Awesome. Thank you.
I have a question. Even more open than his.
Yes.
So the role of physical simulations in graphics is just to present plausible video, right?
Right.
Yeah.
Yes.
But so this is trying to make it easier and more realistic. Now, do you see this going in the other direction? I mean, do you see engineering doing a simulation like that and then trusting that his bridge will not fall? I mean, do you see real physics using this?
Yeah. So, like these days,
Not toy physics for graphics.
Right. Yeah. So, the results I showed today are mostly from 2023, right? But now, my lab mostly actually work on lots of these hardcore problems. Mentioned protein earlier, right? And these robotics situations, they're also like real world scenarios, and also these manufacturing processes. We do a lot of these, chemical experiments, and bending these sheets, and it's the same problem. It's the same question, in the sense that sure you can stick with your classical mechanical engineer solvers, but they don't scale. They're only useful for simulating experiment setup. It's never into production like this, right? So a lot of the things we talk about here translate to there as well. Yeah. No. But again, I think that's like I said in the very beginning, like a feature of my research was my first author paper was actually published on Journal of Mechanics and Physics of Solids. That's the first 4 years of my PhD. So and a lot of it was inspired by problems there. Yeah.
Great.
Yeah.
Thank you.
And sort of the only way for like sort of the question for me was, well, in order for 3D to continuously exist, we have to look at these hardcore problems. Otherwise, 3D, you don't need 3D. You just video models build these films, Yeah. So it's a matter of survival right now. Yeah.
Right.
Yeah.
So we have a question from Thiago.
Yeah.
He said it's a very nice talk, and asked if you have any thoughts on how to improve physics awareness using diffusion models for video generation. That's
Right. So sorry. The question was using physics awareness to improve diffusion model for video generation. Yeah, definitely. Yeah. So we're starting seeing great work in this direction. There are kind of 2 approaches. One is similar to what I talked about today, is you go from videos, reconstruct the 3D, simulate, in 3D, so it has physics awareness. When you
Yes.
simulate 3D, they have physics awareness, then you project it back to the video, right? So, you know, some of these guys at Stanford are working on this direction. One of my students had a 3DV paper on this. So still think you should have 3D. Another approaches, which is, you know, you can, sort of the video model is the foundation model, it's the base model, right? But you can always fine tune it so that it works for your particular application. So for example, you want to be able to control your video model better, then you can train, fine tune your video model using LoRa on some of these video simulation data. So in this case, we're nothing explicit in 3D, just sort of use 3D to generate more data that is sort of physics aware 2D data. So these approaches are all quite exciting.
Yeah. Here's another follow-up question. Like, could 3D be useful in this setting, perhaps to post-training with the simulation?
Right, exactly. Yeah. Post-training, yes. Yeah.
All right. So I guess we can end the presentation.
Yeah, thanks so much.
Thank you very much for
Yeah.
joining.
Yeah.